Today we're going to see a very interesting topic, understanding how derivative causality occurs. Also, I would like to present to you what the solution to derivative causality is, um, and how we could understand the physical ramifications of how it happens, and if we find a solution, how the system is modified as well. We also I plan to talk to you about the introduction to the mathematical solution, not just the introduction, the mathematical solution of derivative causality using the state space form. So here we go. First we have this system that you see here is a CAM follower system. This is the push rod in here. This is a valve in an internal combustion engine, and where you see this is the cam, and of course the cam has a system that follows the profile of this cam. So you have this tap it here, which in some cases is a hydraulic one, but this is the push rod. The push rod is connected to this rocker arm in here, which this part rocks back and forth like that. And of course, what it does is on this point presses the valve, and when it presses the valve, this um, opens it up, on this space in here, and either the valve lets if it's an intake valve, lets the fuel and air in. If it's an exhaust valve, the exhaust gases go out. So here on the right hand side, you have um, the representation, or you may say the idealization in engineering terms, or elements that we are familiar with us to model the real system. And in here we represent the masses for this, the mass for the um, push rod over here, and then with the stiffness, and damping, and this rocker arm we are modeling here as this rigid body with in rotation about a fixed point. And then we have, of course, the valve over here. Can we actually build a bone graft model of this on top of the of this here? I would say yes. I think it would be nice if we actually do that. Right here we can say, oh yeah, let's apply the procedure that we know for modeling by putting a one junction for the velocity of each one of the masses right there, and I put also one junction for the velocity of the input over here, and then one junction for the rotation here, one junction for this mass. That's the first step. Second step is we add the elements that are attached to this. This, of course, is source of flow in here, which is the input. This over here can also be a source of flow, but with velocity equals to 0, because this is the reference over here. This, we attach the I element on the side, which would be, well, let's see. Let's do it to the other side. So it doesn't really matter, but we need the space on that side, so that's why I prefer to do it on this side. So this is the I element over here, and then of course in here also you're gonna have another I element for this mass. We will have this one right here for the rotation. This has J as the parameter in there, and this is the another I over here, and these are the elements that see these velocities as they are described here. In between these two, they are the relative velocities, and we use zero junctions to represent those. The velocity between these two parts is this velocity is this minus this, and of course that relative velocity is seen by these two elements. Now in here the same thing is true. This is 0 here, and then you have a 1 with the C and the R element in here. And the same thing is true over here. So you have this, and then this is a 1 with a C element and an R element over here. Of course, power into the elements, okay? It's good that we do that from the very beginning. So in here, I neglected to put another 1 in here, so I'm sorry, for the velocity of A. In between the velocity of A and this is the angular velocity omega, there is a TF element in here, like that. And from here to here, also another one. This is also another one with a TF over here, like this. And then we have the same situation on this side. So with the 0 and this, we could do the C and the R element over here like this. Same thing. And finally on this side too. And this would be with the 1 with the C and the R element. We could draw this inside. It really doesn't matter. But in reality, this is the way we built the bond graph model, and this would be ready to put into the CAMG software and get the equations and processing and doing the simulation in MATLAB if that's what we would like to do. So let's go back to this picture here. After we have done the model, we can enter that into the CAMG software. This is exactly the model that I just did. See, so that's this one right here, huh? You see, it's the same thing, but entered into CAMG. Now, one thing I want to emphasize over here before we go any further is to have a relationship, one-to-one relationship with this model and this bond graph. You see, this is the rotation consider this with the inertia of this element on this I element. This is the other I. This one is this one. This is the input over here. This in between is this structure here. This in between is this one right here. This one is this one. And the same thing on the side. This is the I element over here. Then you have between the SF and the mass, this other structure, and between this and this, we have this. Any problems with this? No. Any derivative forms? No. Everything is really nice. I am going to cause some trouble right now. This was just to indicate the, in more human terms, you may say, more explicit terms, what each of these elements mean. But that's the list of this slide in here, which I think by now you recognize, even without writing that the I's are the inertia, the C's are the deflection, the elastic deflections and the elastic compliance element, the elastic elements, I should say. And here, what about if we make a change? And instead of representing the lever as we did with one body in rotation, we sort of idealize and we say, oh, look, that system can be equivalent to this one. I do a massless connecting rod and I have two masses on each side. Anything wrong with that? No. I think that it is another possibility, but the situation here is so that we can understand the first derivative causality that this occurs is that think of it this way. This mass, if this mass goes down, what happens to this one? Goes up, right? If this one goes down, this goes up. So there is a total dependency of one or the other. If there is a total dependency of one or the other, wouldn't it make sense that we were represented only with one mass? But since we divide it in two, we say, okay, fine. I represent the velocity of this point plus the inertia right there, no problem. I represent this velocity over here and the inertia right here, no problem. But when I try to complete the causality, this thing is in derivative form. So the first conclusion that we can reach is that derivative form occurs because of the way we model the system. Maybe we need to consider some elements we didn't consider. For example, we can consider some flexibility of this bar, which we didn't, nor even on the first page. Or we can consider that in fact these are not two masses, but only one mass in rotation. That works too. Or if we, like we had it at the beginning. Now, or if we could move this over here and consider just one mass, but the system would be equivalent. That will work too. So the point is that derivative causality is caused by the dependency of one inertia with respect to the other. So it's saying maybe we have one element too many, or we should look into the possibility of lumping these two together to make one inertia that is totally independent. Because if we keep it like this, these two, one is in integral form, and the other one is in derivative form. So let's look at another possibility. Like I said, we take it out of here and we put it over here. Then this I has to be equivalent to the 2 or to the 1 that was the inertia about this fixed axis, considering just one body with rotation about this axis and consider the inertia of the entire body. But if we take this mass and we move it over here, look at the consequence on the bond graph on the right-hand side. Any problem with this? No. So the first thing that we can conclude by doing this move is if you can combine two inertias with one, then you could solve the derivative form. The trick here is, well, we need an equivalent mass, and we cannot just add the two masses. We have to go through an analysis as follows here. If we're going to move this mass over here, the equivalent system must have the same kinetic energy as the original. So that means that 1/2 of mb squared, over here, should be equal to some mass mb squared at A. See? So if you look at the relationship between the velocity of A and the velocity of B, they are related by the lever ratio, A over B, yeah? And if you replace in this equation, in the energy equation, this equation, we will obtain that the equivalent mass is B over A squared times mass B. So the total mass at A will have to be the one that was in there plus this equivalent. And this equivalent is this one, and therefore I-27 in this particular case You see there's this one right here. This one I-27 is the sum of whatever MA was plus this, you may say, translated mass from this side over to here. So like I said, the first conclusion or the first step in curing this is to find an equivalent system. That's one possibility. We could also add the stiffness of the bar, and that would also uh, alleviate this problem. But we are testing now and trying to learn what does derivative causality mean. And the conclusion we have just reached, it means the dependency of one inertia element over another. So, or say with another. Here is the displacement, the display in CAMG, and here you can see the I element that is in derivative form. CAMG will flag your red. It will make the elements red to say, oh, take a look at this. Do you really want to proceed like this, or do you want to modify your system? Of course, you have a choice. One is to modify the system and consider other effects like the deflection of those parts, to consider the spring constant, and the other one is consider damping. So you consider those two things, but mainly the spring constant will be very instrumental in affecting this derivative form. So in this case, what I did is I said, okay, we have to find a solution. And the reason we want to find a solution, the way I should say that we want to find a solution, is by isolating the top of that system. Let's not worry about the bottom side, but only let's take this one that has derivative form and work with it, okay? So CAMG, if you go to the file and then it has the option that says equations. We're interested on the equations of the system. So on the right-hand side are the CAMG produced equations for the system. See, right here. Okay, so in this particular case, you notice there are two extra equations. I shouldn't say, well, no, extra, two equations that are different. This one that says that the derivative of dp sub 6, E6 is dp sub 6. And then this one right here, psi 6 times f sub 6. So in this case, you see, I could use these equations and reduce it to the Cauchy form. So instead of having a bunch of little equations, now we are gonna substitute the different contributing equations to produce the Cauchy form. When we produce the Cauchy form, we notice something very unusual. You see, you have in here the original 3, the C, the 2 C's, and the I that produced this causal form. But then you have this dependent causal form, and in here is the derivative is calculated on the right-hand side, and so is in here. Problem with this approach is that computers are not very good to differentiate. They are very good to integrate, but not to differentiate. So you could understand why, because if you find the slope going to infinity, then obviously that would overflow and it won't work. So now we are left with a challenge here. If we have this Cauchy form, what can you do? What can we do to first get all the derivatives on the left-hand side? And second, what kind of mathematical transformations do I need to make? So after giving it many, many hours of thought, I said, look, this is the state space form for a normal system. Right now, out of this, CAMG has given us these equations. Question is, can we solve the derivative form problem? Okay. In this case, this is the mathematical solution to that problem. You have x dot is ax plus bu, but in here, it has e times, this new matrix e times x dot derivative is what it means over here. So x dot derivative in this case would be this d piece of 6, and that is the one that caused the derivative in this case. So and that xd would be matrix F times the vector of the state variables. Okay, so here we have, this is the heart of the matter over here. And here you have the equations, original equation plus this derivative on the right hand side. So not to lose perspective, this one. And then you have the definition of the variables in here, the ones in derivative, the derivative form. And then you know that you could replace this into here, and that's exactly what we do. So we have these two matrices, E and F, but they are multiplied by this x dot over here. So one way to solve this is to move this on this side. And once we do that, we continue and we could find out the eigenvalues. We can find out the derivatives in here as a factor right here. So I minus e times f. And to eliminate this and just leave it in explicit form, let's multiply by the inverse on both sides, and this is what we'll have on the right hand side. See? So modify the I, the E, and the F matrix, but this is the way we find the new state space form. I call it A nu plus B nu, and that would be 1 minus E times F multiplied times A, and B would be 1 minus E times F multiplied by B. Okay, so this A and B are this new A matrix, and they come from these products, just so that you remember. Once we have done that, we have obtained, let's say, this is the derivative form, and you have this one in here, and then you have an example of this. This is without derivative causality. And this one, if we add this, wow, matrix of the system with CAMG in derivative causality. Okay, so this is the matrix now. But what about now? If take a look at it, I kept messing the system up much more so than at the beginning, because I wanted to show you that if you connect two masses here and also you connect two masses here, you really messed up the system, because you are saying that the motion of this one determines the motion of that one, right? It's very obvious. If you move this, this is going to move. I mean, granted you that you know the point A, whoever is in in charge here for the for the for the point A in here and B in here being like this produces this derivative form, and by doing this produces another derivative form. But the fact is that you see, what am I saying with this? I'm just saying that one depends on the other. By putting that push rod, I mean, this solid rod, I am telling the system, look, this looks like two masses, but in reality is only one. Do you see my point? If you put this rigid link, you're saying, yeah, these two would move together, and they are not independent. One depends on the other. That's what we were saying. But by doing this, I complicated this, and then I did something worse. I added one spring on the side, which is, one after another. That representation here resulted in a derivative form that was, yeah, it's a derivative form for this system. So in here you have the uh, a similar situation as here, because you have in here, by adding this other spring, produce a derivative form over here. In reality, there is only one damping, but I mean, yeah, only one C element, but we can make it two, and then you see clearly that he's got derivative form over there. So if you have it like this, with four derivative causalities at once, doing the problem by hand is not going to be pleasant. So if you put it into the QMG software, it predicts all three, no problem. And this derivative causality, and here you can also modify well, like we already said, we can modify the equations, but in this case, you have four derivative causalities. So what I did is I went to CAMG and say, okay, look, I need those derivatives, and it gave it to me. Okay, so this is how we solve the derivative form, by using these new matrices E and F. But you see, if we sort of prune this out of the stuff that is bothering us, and we look for equivalent inertias, we can come up with this, because you would not need to know equivalent inertias um, unless your system has these derivative forms. Otherwise, if you have this, you have eliminated those and concentrate on the xi, then that's okay too. But we just need to be careful uh, how we handle these derivative forms, and how we take one out and make it equivalent to the other, like in this case. Now, if you take a look at the bond graph modeling here, and you obtain the state variables right here, the vector of states is this PQ is called vector of states, and then you have the matrix over here, that results in the calculations. Now in here, okay, in here you see we apply this I minus E times F inverse multiplied by A, and then we have, if we do this, we have the solution to fourth derivative form. Okay, so you have the two inputs in there, and then you have this U, and so B times B is these are the new matrix, this is the new B matrix. So you can see that the new B matrix became much more complex, but that's what we need. We need this to solve the system of equations. So in conclusion, you can actually modify the system a little bit, or if you insist, it'll produce a set of implicit equations that needs to be solved, as I have shown you here.